Okay, so last time we discussed about the Laplace transformation, and we derived or we determined the Laplace transform of some of the elementary functions, of course, utilizing the definition. So if you remember the definition, it's the integral of e raised to negative st times the given function, integrating with respect to t with limits from 0 to infinity, and evaluating that function, okay, integral transform, we were able to have the following formula, starting with the Laplace of 1 is equal to 1 over s. The next one, the Laplace of t raised to n, where n is positive, okay, real numbers, so 1, 2, and so on. And the Laplace transform of that is equal to n factorial over s raised to n plus 1. The next one is function, which is e raised to at, where a is a constant. And the transform for this is 1 over s minus a cosine bt. So you have, so it's s over s squared plus b squared, where b is a constant. And the next is sine bt, which is the Laplace transform of this function is b over s squared plus b squared. Now, in terms of the hyperbolic functions, hyperbolic cosine of bt is equal to s over s squared minus b squared. And hyperbolic sine of bt is equal to b over s squared minus b squared. So today we will be talking about the properties of Laplace transforms. First property is linearity property. If a and b are constants, f sub 1 of t and f sub 2 of t are functions whose transform or whose Laplace transform exists, then we can follow this property. So Laplace of the given function, okay, f sub 1 of t plus f sub 2 of t, we can actually determine the transforms of each term. So taking note that a and b are constants, so you put the constant before the operator, the Laplace operator. So we have a Laplace of the first term, which is f sub 1 of t. So again, we use this operator. The grouping symbol that we use for the Laplace transform is the braces. Plus the second term, so b is a constant, so you put that before the operator of the Laplace. So we have b Laplace of the function f sub 2 of t. By utilizing a definition of the Laplace transform, the Laplace of the kernel e raised to negative st times the given function, integrating with respect to t with limits from 0 to infinity. So here, the first term, we have, okay, using the definition, so we have the integral of the kernel times the first term, f sub 1 of t, plus b, integral of the kernel e raised to negative st times the second term, the function in the second term, okay, times dt, or simply, the result is easily extended to more than two functions. So it's not limited to two terms. It may be three or more terms. Okay, and because of this property, Laplace transform is also known as a linear operator, and it has a linearity property. Let's be clear here. I'm going to write, say for instance, you are to determine the Laplace transform of sine of t times cosine of t. Okay, it says that Laplace transform is a linear operator. So you cannot just say, since you know that the Laplace transform of sine t is 1 over s squared plus 1 squared, or 1, and the Laplace of cosine is s over s squared plus 1. If you encounter this kind of problem, do not multiply their transforms. It is not allowed. So you cannot multiply these Laplace transforms to determine the Laplace of the product sine t times cosine t. Instead, you think of an appropriate identity for trigo function, just like this one. So remember that sine of 2t is equal to 2 sine of t cosine of t. So you recall this one. It means that this sine t cosine t has an equivalent, of course, dividing both sides by 2. So we have sine t times cosine t is equal to 1/2 sine of 2t. Using its identity, we can be able to determine the Laplace transform since we cannot multiply their transforms. If you can see two different functions, elementary functions being multiplied. What you will do here is 1/2 is a constant, so you put that before the operators, so 1/2. And then the Laplace of sine 2t is sine, so constant muna, the numerator is b, so that is 2, over s squared plus 2 squared, or in that case, it is 4. So you cancel 2 here, 1 over s squared plus 4. So that's the final answer for this Laplace transform. You can only get the Laplace of each of the terms. So for example, there are 3 terms. So take the Laplace of the first term plus Laplace of second term plus Laplace of third term. Again, this can be extended to more than 2 terms. So we have the first example here. Find the Laplace transform of the function f of t equals 2t plus 3. This function has 2 terms. Then what we can do here is to take the Laplace of the first term plus the Laplace of the second term. This is the resulting equation. So the first term, Laplace of 2t, so you can put the constant 2 before the operator since it's a constant. The same with the second term, because you know the Laplace transform of 1 is 1 over s, and the Laplace of t is 1 factorial, since t has a power 1, so 1 factorial, or simply 1 over s raised to n plus 1, or your n is 1, so we have s squared here. So then you arrange your final answer. If it is not that complicated to put into a 1 fraction, then do it. So this is your final answer, 2 plus 3s over s squared, where you simply factor out 1 over s squared. And this is your final answer. So either of these two. Okay, now let's go to the next property. First shifting property is, of course, the introduction of an exponential function e raised to at. If you have a function f of t and then multiplied to e raised to at, as you can see, the result has s minus a in it by definition. So e raised to negative st times the given function. And then, so we did this, f of t is equal to e raised to at. We have derived already this one. So the Laplace of the function times e raised to at will give us, instead of writing s, you have s minus a in it. Let me just present to you again the formula or the elementary functions with e raised to at in it. Say, for instance, the function t raised to n is multiplied to e raised to at. So remember, t raised to n, the Laplace transform of this one is n factorial over s raised to n plus 1. But because it has e raised to at, and this is first shifting property, so instead of writing s, you have s minus a in the denominator. The next one, okay, so remember, so just let's cover this one. If it's cosine bt, it will be equal to s over s squared plus b squared. But since we have e raised to at multiplied to this function, so that s will become s minus a in the denominator as well. So you have s minus a squared. And for sine bt, okay, for the Laplace transform of sine, you have b over s squared plus b squared. Since you have e raised to at, so it will become b over s minus a squared plus b squared. For hyperbolic function, so the same idea, the numerator will become s minus a over the quantity s minus a squared minus b squared. And for the hyperbolic sign, you have b over the quantity s minus a squared minus b squared. Now let's have some examples here. So find the Laplace transform of f of t equal to e raised to negative 3t times cosine of 5t. As you can see, you have an exponential function here. Instead of using the definition, so we will directly use the formula. So Laplace of cosine 5t, remember that it is s over s squared. What is b? B is 5, so b squared. So we have 5 squared here. But we have an exponential function e raised to negative 3t. So by using a equal to minus 3, we plug in the formula that I presented to you earlier. So instead of writing s, you put s minus a. So s minus negative 3, we have s plus 3 in the numerator over s plus 3 squared plus 5 squared. Okay, and then finally, we have s plus 3 over s squared plus 6s plus 34. So y s squared plus 6s plus 34. So we expand this factored form. So we have the square of the first term, so s squared, twice the product, so 2 times 3, 6 times s, so 6s, and then square the last term, so we have 9 plus 25 is equal to 34. That is our final answer for example number 2. Example number 3, find the Laplace transform of the given function t cubed times e raised to 5t. So this is an elementary function multiplied by an exponential function. So applying the first shifting property as well. So recall again that the Laplace of t cubed is 3 factorial. Okay, the n here is 3 over s raised to n plus 1. Okay, and that is 3 plus 1. So we have 3 factorial over s raised to 4. And 3 factorial is equal to 3 times 2 times 1, and that is 6. Now, because of e raised to 5t, we have a equal to 5. The resulting transform is 3 factorial over s minus 5 raised to 4. Okay, so you need not expand this denominator. So it's okay that it's in factored form. Just write the value of the 3 factorial. So our final answer will be 6 over s minus 5 raised to 4. Example number 4. Okay, so here, remember that the Laplace of sine of t using the formula 1 over s squared or b over s squared plus b squared. So we have b equal to 1. The Laplace of this function is 1 over s squared plus 1. However, you have an exponential function e raised to minus 2t. So your a here is equal to minus 2. That's why your s will be replaced by s plus 2. Okay, now in this case, since you have plus 1 here, you can combine the constants if you expand s plus 2 squared. Square the first term, twice the product of the first and second term. So you have 2 times 2, 4 times s. So we have 4s. Square of the last term. So 2 square is 4. 4 plus 1 is 5. So this is now your final answer for example number 4. Okay, example number 5. Find the Laplace transform of 4 hyperbolic sine of 3t minus 18 times e raised to minus 5t. This given function has 2 terms. So we can determine the Laplace of the first term and then take the Laplace of the second term. So we can rewrite it in this form. So 4, you put that before the operator Laplace, and Laplace of hyperbolic sine of 3t minus 18, you put that before the operator. So we have minus 18 Laplace of e raised to 5t. As you can see, we have a formula for the Laplace of the hyperbolic function. In this case, hyperbolic sine bt is equal to b over s squared minus b squared. And the Laplace of e raised to at is 1 over s minus a. Now, applying the formula, of course, we copy 4 and then the Laplace of hyperbolic sign. So we have 3 over s squared minus 3 squared minus 18 times the Laplace of e raised to at is 1 over s minus negative 5. So in this case, we have our answer to be 3 times 4 is 12. 12 over s squared minus 9 minus 18 over s plus 5. We can combine them into, can put them into one fraction. So 12 times s plus 5. So we have here 12s plus 5 times 12 is 60. So minus 18 times, s squared minus 9. So you have minus 18s squared, and negative 18 times negative 9 is we have positive 162. And our final answer would be, so you can copy this as is. This is in factored form, or you can multiply them together. So by arranging the s into the highest degree, so minus 18s squared plus 12s, combining all the constants, so 60 plus 162. So we have, and that is 222 all over s squared minus 9 times upon ts plus 5. Okay, finally, we have example number 6. Okay, find the Laplace transform of cosine squared 2t. So as you know, it has a power. There's no direct formula for finding the Laplace of this trigo function, right? Again, we cannot apply linearity property if this is the form, or just, you get the Laplace transform of cosine 2t and then multiply it twice. It's not allowed, okay? You cannot multiply, two cosines, the transforms of these cosine. Instead, you think of the identity for this trigo function. So remember that the cosine squared 2t, its identity is equal to 1/2 times the quantity 1 plus cosine twice the angle, right? So 2 times 2t, which is 4t in this case. Now, as you can see, it has two terms. Then you can apply linearity property. So you have two terms. The first term would be 1/2 Laplace of 1 plus 1/2 Laplace of cosine 40. Okay, so the Laplace of 1 is 1 over s, and the Laplace of cosine 40 is s over s squared plus 4 squared. Now, putting them into one fraction, so we have here 1 over 2s plus, so this one here, we have s over s squared plus 4 squared. So just to show you why it became s squared plus 8 over s times s squared plus 16, let me get my pen. So we can factor out 1/2 and combine the 1 over s. So say here, 1 over s plus s over s squared plus 4 squared is 16. So cross multiply, so we have s squared plus 16 and plus s squared. And the denominator will be s over s squared plus 16. Since we have here 1/2 and then we factor out 1/2 here, so you put 1/2, and then here you can combine like terms here, so s squared plus s squared. So we have here, let me change the color, so we have 2s squared plus 16. And you can also factor out 2 there, so 2 times s squared plus 8. But since this is, or it is a factor also na 1/2 dito, so we can actually cancel 2. That's why the result is this one. Okay, s squared plus 8 over s times s squared plus 16. So for your seat work number 3, find the Laplace transform of sine squared 2t. So we did sine squared cosine squared 2t. Now you do the Laplace transform of sine squared 2t. And then for number 2, t raised to 4 cosine or hyperbolic cosine of t. So I already introduced to you the identity for hyperbolic functions. So just to recall again,